final AP Physics lesson of the year. And for a lot of you who are seniors, it's the last time you'll have to interact with me. So here we go. These are my final hints and tips for your success on the AP exam, and these are slightly modified based on the coronavirus edition of the exam this year. First of all, your most important job is not to get the answer right. I know it feels like you want to get the right answer, but that's not your most important job. Your most important job is to demonstrate you understand and can explain and apply physics. So all of the rubrics, the graders, this is what they're looking for. They're looking for a demonstration of understanding. They are not looking for the right answers. The graders aren't impressed with the right answers. They've seen the right answer a couple thousand times by the time they get to your exam. They are just trying to determine, based on a rubric, to what extent you have demonstrated understanding. Okay, so don't focus on the answer as much as focus on demonstrating that you understand what's going on. So if you see a problem and it involves a satellite going around the Earth, make sure you demonstrate that you understand that centripetal force equals the gravity force and what that means and what cancels as you work through it, okay? So keep that in mind. The next thing, make friends with the grader. The grader has graded an endless number of these things. Thousands and thousands. And so first impressions matter. So when they see your paper, if it looks like a total mess, it's torn, it's ripped, there's paw prints on the upper corner, they're going to think, this guy didn't even care. Why should I? So get neat, clean paper. Get 4 sheets. You're going to have 2 problems. You probably will only need 1 sheet per problem, but go ahead and plan for 2. Put your AP number and your initials at the top of each page, and then number each page. So page 1, page 2, and then for question 2, page 1 and page 2. You may not need it, but if you need that second page, it'll be ready to go. All right? And you're going to be pressed for time a little bit at the end of these. So one less thing to not worry about is thinking about grabbing a second piece of paper and keeping writing there. Graders are just people like me. They're physics teachers, and we use standard symbols and notations. And when you can use those standard symbols and notations, you demonstrate that you have some familiarity with the whole idea of physics. So don't make up your own symbols. We use T for time. Don't put at the top of your paper Q equals time and then you use Q. Although that's technically correct, it's confusing. So just use the standard symbols notation when possible. When you're sketching graphs, make them neat, label the axes, put a title on there if possible. Just make it all nice and organized with the ruler. Keep your solution organized, part A, part B. If there's subparts, A1, A2. Keep that all organized for the grader so they can clearly see what's going on. As you organize your work from top to bottom and then go to the next page. Don't try to squeeze stuff in. If you've got 3 more sentences to write, don't, avoid the temptation to go shove it up there in the top on the right-hand side where there's a little bit of empty space on your page. Go on to the next page. It's there and waiting for you. Use it. You don't get any bonus points for squeezing your solution to the smallest possible space. So use lots of space to make it clear exactly what's going on. And generally, we work from top to bottom and left to right. So as you're reading the questions, pay attention to the verbs that are used in the prompts. You'll see various verbs. It might say calculate, or compare, or derive, describe. Estimate is a tricky one. We ran into that on a couple of practice problems. If you have a really small force attached to a really large mass and you're asked to estimate the acceleration, you can say it's close to 0. So estimate means they're not expecting a long calculation. Don't waste your time. They want you to think about just sort of an approximation, okay? Explain, justify, label, plot would be a graph, and then sketch or draw are probably going to come in if there's free body diagrams. So just make sure you know that on each part of the question, you know what verb is being used in the prompt, so you know how to properly respond. And it helps to underline those verbs as you're reading the question, but just keep those in mind. So we've talked about this all year long, but before you use the physical principle, state the principle you are using. You can state it in words. You can say energy is conserved before and after, or energy is conserved as the block goes down the slide, Or you can say ME final equals ME initial with symbols, but it's almost always worth a point to identify the principle being used. And if you don't identify the principle being used, you don't get that point, even if you have the right answer, because you haven't demonstrated you understand the big picture of physics. So think about what principle you're using, and then state it first and work from there. So it helps to read through the entire question so you get a feel for what is being asked in each part. A lot of times there'll be a setup, some kind of, a ramp is constructed on a table and a block starts at the top and it slides down without friction and then it's launched into the air and then it lands and there's like, and then part A will ask you to do something and then part B will ask you to do something. And so just kind of read through the whole question before you jump in and start answering part A in way too much detail. For example, part A might ask you to make a prediction. Or just explain something without equations. And part B might then ask you to derive the expression. It's good to know what you're expected to do in that part by kind of looking ahead to see what the whole question is about. And also sometimes if you're more comfortable with the equations, it might help to do part B first. So go to part B and derive the distance it goes or whatever it is, and then go back and see if you can put that together in a coherent prediction or explanation without the equations in part A. So just keep that in mind, read through the whole question. This is also going to help you manage your time because part D might be something you really know how to do, but if you don't read through the whole question, you may not have time to get to it. So it helps in your time management if you kind of get the big picture of what's going on here too, okay? So just read through the whole question, highlight the verbs, kind of get an idea of what's being asked in each part, and then tackle it. So when you're asked a question and it says, explain your reasoning or explain, anytime it has that in there, remember our CER process, okay? So remember, C stands for claim, make a claim. Which block hits the ground first? So say block A or block B, make a claim. Provide some evidence. What evidence do you have that leads you to this claim? So what is it about the problem that makes you lean in that direction or not? And then lastly, and maybe most importantly, give a reason why the evidence supports your claim. Okay, so let me switch screens here and see if I can show you an example. If I have the sun right here, and I have 2 points in the orbit of a comet. So a comet is going around the sun. At which point is the force of gravity stronger? And so you have to make a claim. So the claim is that gravity is stronger at point B. And you should actually write this out in a couple of words. But that's my claim. Now, what is the evidence? Well, the evidence is that point B is closer, right? That's the evidence from the picture. Point B is closer to the sun. But you haven't finished because if all you say is gravity is stronger at point B because it's closer, you haven't done everything. You've got to think about a reason. Why does being closer mean the force of gravity is stronger? And so here's where you need to invoke the fact that the universal law of gravitation, m1, m2 over r squared, is an inverse square law. The fact that it is a smaller distance means that it is a bigger force. Okay? So when you think about an explanation, make a claim. Think about the evidence presented in the problem. So ball A starts from a higher point or something like that. And then especially think about the reason. What is it about that evidence that makes the claim true? Okay? So that's what we mean when we say claim, evidence, reason. And we've practiced this all year long. But just keep it in mind, all right? Okay, this one crops up more than you would think. It's especially bad in the mathematical sciences, calculus and stuff, but it happens in physics too. Please avoid vague antecedents. Don't say it. It lands first. It may make sense in your mind, but to the grader, they're not sure what it refers to. And if it's ambiguous, they're not going to give you the point. So say ball A lands first or ball B lands first. Just try to avoid the word it, okay? There will be an experimental design question, possibly. An experimental design is where we see whether you understand how to construct a basic experiment. And we've practiced this a lot. My only complaint here is that repeatedly I get use a video camera to collect the data. That doesn't count. Don't cheat by saying use a video camera to collect the data. Demonstrate that using video cameras is absolutely valid, and you can use that as part of your experiment. But please demonstrate that you understand that what a video camera is doing is it's recording the position and the time in every frame. And it really only records the position if you have a meter stick in there too, right? So you need to show that you understand how to use the information collected from the video camera to get whatever it is you need. So if you're trying to find the velocity of a ball before and after it collides with the ground, don't just say use a video camera to collect data. Say use a video camera to collect the position and time every frame before and after the collision, and then using the distance and the time, the position and the time, you can calculate the velocity before and after the collision and determine whether energy is conserved. Okay? So just make sure you understand that a video camera isn't a magic box that just collects data for you, but that it's just a tool we use. Also, I want you to think about the relationships that are involved to determine what you need. So, for example, if the question asks you to design an experiment on an unknown planet to measure the acceleration due to gravity by dropping rocks or something, you would need to think about the relationships involved. And so that might look something like this. If you're dropping rocks, it's not too difficult to measure the time it takes for the rock to fall. So you might drop a rock from here and let it fall and hit the ground. And so what you want to think about is the relationships. The distance the rock falls is going to be 1/2 the acceleration due to gravity on that planet times time squared. So if you dropped it from several different distances and you measure the time it takes to fall, then you could plot the time it takes to fall squared on one axis, the distance from which it was dropped on the other axis, and for different distances you would get different points, and you could use a line, and the slope of the line would be 1/2 the acceleration due to gravity on that planet. So think about the relationships that are involved when you're trying to design an experiment to accomplish a task, okay? And also, when you're designing an experiment, you never want to rely on a single data point. So don't just say, I'm going to drop a rock, measure the time it takes to fall, and calculate the acceleration due to gravity. We want to do this several times because any given point might have some uncertainty in it or some error. So by doing multiple different distances or multiple different trials, you can minimize the variability or the error in your measurements. Okay? So that's what we mean by when we say think about the relationships involved to decide what data you would need to collect and how you would collect it and what you would do with it to get the information that you need. All right? Okay. Another kind of question that's common is the paragraph length response. So you might be asked to respond with a paragraph explaining something or explaining why Susie's right and Philip's wrong or something like that. So just keep in mind, a paragraph here means a coherent argument. We're looking to see whether you can put down some thoughts in a logical order. You can use words. It's not just a writing assignment. And so for this reason, please, please, please use paper. Solve your problem on paper and then take a picture and upload it. Don't try to type this in an editor and then copy and paste it. Physics is too symbolically weighted to be able to really do that effectively. So remember, use words, but also use equations. You can make some calculations. Diagrams are awesome. Graphs help. Anything you can do to convey or explain are valid for this paragraph length response. So here, paragraph doesn't mean words necessarily or only, but an argument, okay? If it says paragraph length response and all you have is equations and calculations, you will not get full credit. All right, so we are looking for some words to help string along. Words alone aren't required, but equations alone are not allowed. So you need to kind of make an argument here with some words and string it together. Here's what AP says the goal of a paragraph length response is. The goal is that the student should be able to both analyze a situation and construct a coherent, sequenced, well-reasoned exposition or argument that cites the evidence and the principles of physics. So we're looking to see, can you demonstrate in a paragraph response that you understand what physics is, how it works, and how to apply it. All right, so keep that in mind. All right, two last topics, the most important topics, probably. The first one's energy. So I just want to quickly review the big picture on energy. When we are dealing with the motion of a single object, we're generally going to use energy. Okay? So if you've got a single object, a ball, a block, something, and it's doing something, your first inclination should be to think about energy. Okay? Energy lurks in 5 places in a problem. There might be kinetic energy at translation. So if the object is moving, if its center of mass is moving, it has translational kinetic energy. That's 1/2 mv squared. If it is rotating, it also has some energy due to its rotation. So some of its energy will be rotational kinetic energy. Energy might be stored in the gravitational field if it moves from a higher point to a lower point or a lower point to a higher point. So potential energy can be involved, and that's m times g times h if it's near the surface of the Earth. And energy can be stored in springs. Okay? And there's 5 places. So what's the 5th place? Well, energy can be transferred into or out of your system by external forces. So if you have, for example, a ramp and a block slides down, blocks are nice because you know they don't rotate. So you're not going to have any rotational energy. If this block slides down the ramp, then when it gets to the bottom, all of the potential energy that it had due to gravity becomes translational kinetic energy. But if you put a ball on the exact same ramp and it rolls without slipping, when it gets to the bottom, it'll have the exact same energy as the block, but it won't be moving as fast because some of the energy will be in the rotation of the ball and not all of it will be in the translation. So just think about whether it's a block or ball, whether it's rotating, which means some of the energy will be in rotational kinetic energy, or whether it's just sliding. And of course, if there's friction, you're going to be losing some energy. And how much energy you lose due to friction depends on the force of friction times the distance it acts. So remember, the energy transferred, the work, is the force times the distance. And if it's friction, this will always be negative. You'll always lose energy. And if you've got some goofy problem where you've got a spring attached to a plunger and it makes the ball go zooming, then the energy stored in the spring will become energy stored in the block as it's moving. And if that thing was attached somehow to a ball, which was then rolling, then of course all the energy in the spring becomes energy in the ball, but the energy in the ball is now split between translation and rotation. So it won't be moving quite as fast as the same massive block there. Okay, so just keep those things in mind. They're important ideas. And my best guess is that one of your questions is going to deal with energy in some form. The second and sort of next biggest idea that kind of weaves its way through the entire course is momentum. And so you know momentum is going to be involved if you deal with the motion of 2 objects. I can't imagine more, but 2 objects. So when 2 objects interact, we use momentum. If there are external forces on the system, so something's pushing on one of the blocks, if it's not on a table that's not level, or if there's friction, if there's an external force on the system, then the momentum will change, and that will affect the motion of the center of mass. Okay? But if there's no external forces, the total momentum is conserved. So momentum before is equal to momentum after the collision. And the motion of the center of the mass does not change. So if the center of the mass is moving at 2 meters per second, it'll be moving at 2 meters per second after the collision as well. All right, so those are some big ideas. We spent a lot of time going through all the details and practicing, but just kind of want to remind you that if you're dealing with one object, a single object, you're probably using energy. If you're dealing with 2 objects, you're probably going to deal with momentum. Okay? All right, so lastly, your exam is at 4 o'clock. Please log in at 3:30. Make sure you're all ready to go. Make sure your browser's been updated to the latest version. Make sure you've got your reference pages printed and ready. If you need any help with that, please just email me. I'm sitting around waiting to help. So you're well prepared. You know your physics. I taught this course for many years, and we've covered everything you need to know to do well on the exam. So take heart in the fact that you know what you're doing. Just relax and do your best. Don't be too stressed about this. If you're going into any kind of science or engineering, you're going to take more physics in your future. So it's not like if you miss something here, it's going to end your career. So just relax. This is a very novel format. There's only 2 questions. I spelled questions wrong, whoops. With such a novel format, the pressure is really off of you and it's on College Board. Because without all the multiple choice questions, without the 5 usual questions, it's very hard to tell whether a student has a full understanding of physics or not. So the pressure is not on you, it's on the College Board. So just relax. Do your best, take a shot at it. I'm told that there will be lots of 3s, 4s, and 5s. They're not going to try to restrict them this year because of the small test. And then lastly, if things do go badly, don't worry. We'll just blame it on the coronavirus, e-learning, all that stuff. Nobody's judging you. This is a chance for you to show that you're well prepared, you understand physics, and if it goes badly, there's really nothing lost. So don't be stressed. You'll do well if you relax. The best thing you can do is get a good night's sleep. Sleep in tomorrow a little bit so you're well rested when it comes time to take the exam at 4 o'clock. Have yourself some caffeine, and in an hour it'll all be over. Okay? Let me know if I can help you in any other way. Good luck. You guys are well prepared and you're going to do great. Thanks.